Okay. Good evening, everyone. So from today, we begin the last 3 sessions of our course, which will deal with unsupervised learning and generative learning or generative modeling. That is also unsupervised learning. Still now, we have been doing a class of models that was predicting P of y given x. So given x, our model, what it was doing, it was predicting y, right? So which class it belonged to. Right? Which class or the regression value? Yes or no? I hope
Yes,
now from today, we'll say that in reality, what happens is, so for today, we'll be doing only clustering algorithms or unsupervised learning algorithms. Next class, will do dimensionality. So today, only one class will do clustering or unsupervised learning. So that is a big deal in itself, but the concentration of this of our course of our syllabus is not that much on unsupervised learning because it's more a research topic than a well-known science at this point. So we have many neural networks that do unsupervised learning. You may see ChatGPT there. When you do when we do advanced courses like NLP, we'll see how unsupervised learning is used to train these words that you see today, a word embedding large language models like ChatGPT. So those are different philosophy altogether, but today we'll be doing the tried and tested, what is there in your syllabus and what is generally taught in undergraduate courses related to unsupervised learning. We'll do a bit more of that. Like we'll be concentrating more on hierarchical clustering and K-medoids, which is generally not done, so that you are well off and you know all the type of clustering algorithms. This is the wide range of all the clustering algorithms that are actually there in the literature. Other than that, all are neural network based algorithms. So this was a brief overview of what we have done. So till now we have done what is called uh, we have what have we done? Just one moment. Uh, is this Yeah. So till now, what have we done? We have done this class of algorithms called supervised algorithms, like supervised models, supervised learning. So in supervised learning, what was the fundamental idea of a supervised learning? You had X and you had the labels, right? Labels and you had features, and your work was to predict labels, correct? This was supervised learning. In unsupervised learning algorithms, what we try to do is we have no labels altogether. Here, we have no labels. We have only data points. So the intuition comes from what humans do. So what humans do, you see all around us. We generally, all the times, we are not trained with a output. For example, if we are told, you may have seen in your childhood that you may have, once you have learned a mathematical rule, say you have learned uh, 1 to 10 or 1 to 100, you would essentially be able to cluster or essentially be able to, in an unsupervised manner, tell what the next number would be. One example would be this. For example, once you had, when you're growing up, you could easily categorize between cats and dogs. You may not have known the names of cats and dogs, but today if you see a new animal, you will be able to categorize animals of the same kind together, right? So for example, see, look at this picture that I've drawn over here. So think of these are three animals whose names you do not know, but once you are able to see few animals, you will be able to say that these animals are similar. So lions, for example, would be similar. Then tigers would be similar. Giraffes would be similar, right? Are you getting the intuition? So you may not know the labels, but you would be able to tell me that these animals are similar, these are similar, these are similar. You could be able to separate them, right?
yes,
So that is the are you able to understand the intuition of unsupervised learning? So you're not told the labels of these algorithms, but you would be able trying to tell that which of these your algorithms, which of these like broad variety of features does these have in common. For example, say a class 1 object would have some features in common, and you would use those features to say that these are, say, tigers. Tigers would have whiskers, lions would have manes, and you would be maybe using those features to say that these are similar category of objects. You may not know they're lions, but you know that they're similar. Similarly, you may say tigers, these are tigers, they're similar. Right? But the question arises, how do you do that without labels? Till now, we have been using labels to do all these type of learning algorithms. So can you tell me, so you can read the things that I've written, but I'll be deriving it now. I'll give you the intuition in a better way so that you can understand. So say you know that there are four animals in a jungle, four type of animals. They have features. So these are their features. So animal one, this is the other feature of the animal. This is animal two. Then you may have this is just cartoon. In reality, there would be more overlap between the features, but just for illustration purposes, I'll be drawing them as I'm drawing them now. Okay, so there are four animals. So the idea is the features of similar objects must be similar. Do you agree? Otherwise, how do you say they are? Now the question what features we are using is a different question altogether. Say the features are good features. If the features are good, if the features describe these objects well, then do you agree that the features of similar animals should be close to one another compared to animals which are far away from one another? Is the intuition clear?
Yes.
For example, you can take height and weight as the features, or you can say mane, length, and width and height as the other. So you will be able to say that the features are going to be together. So do you agree? If I have a representative element, so I'll be naming this as say one big circle. This is the representative element. Say I name this. So I'll be naming this say C1, class 1 or cluster 1, whatever you want to call it, C2, C3, and C4. Now I tell you, I have one data point that I can use. So it's not yet come, yeah. So now I tell you, I have one data point in each of these category of objects, which I need not definitely know the names of, but I know there are different categories of objects. If I have one marker of a category in that space, say for example, I'll be putting some cross over here, say cross over here, and say I name this as mu1. Similarly, I will have one more object, okay, mu2. Similarly, I have another representative element over here, mu3, and I have one element over here, mu4. So what should be the idea of this algorithm? Do you agree that the distance between the points on inside these category of objects, which we'll be naming as clusters from the time from now onwards, should have a small distance to this, to these means that you have? So this representative element, if your representative element is good, then you would be able to say that x minus mu I sum over x belong to this cluster I equal to 1 to k cluster should be minimized. Yes or no? So instead of writing mu k, we can write c1, c2 dot 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 ck. See, these are the clusters. So my idea is just don't think about what I'm writing in math form. I'm telling you So these clusters are set of objects, right? X1, say C1, X2, C2, dot dot dot, Xk, Ck. Okay. So they have k objects belonging to that cluster. Do you agree? So say this is one similarity measure. Distance is a similarity measure. So lower distance is a good similarity, right? Distance decreases, similarity increases. Are you following? So do you agree that when you have these representative, these mu's that represent these classes, the best mu's would be obtained when the distances to each point in those clusters is minimized? If I take a mu over here, another mu over here, will it work? These are bad representative elements, right? Do you agree?
Yes.
So wherever, so these points which I have drawn as mu1 to mu4, these are the best ones because they are the sort of the centroids of the clusters. That's what I'm trying to come to. Do you agree that centroids of the clusters are at the minimum distance from all points? Yes. So this is just an idea that I'm trying to convey. So the best points that you will have is for each of these clusters, you will try to have each of the centroid of these clusters to be the representative element. And why do I need a representative element? This is because when I have a new data point, I will be able to say which representative element is it closest to, right? It is one way of saying. Another way of saying is it will help you to cluster the data points itself. We'll see why. Okay.
Like means the summation thing we have written that will
Yes.
return the clusters.
It will return the clusters. So the optimization is over Ci. Don't think about the math so much. It is going to give you the best clusters. So it is not going to give you means. Means will come at us as a byproduct of the clusters, right? Because means will become the centroids of those clusters.
Acha, acha, acha. Okay.
So Ci's are set of, like this, ask these questions. Now, set of all, I would not have written this thinking this was trivial. Set of all objects belonging to cluster I, right? So you have to select all the objects that will belong to cluster I. You can also put mu1 to mu k if you want, right? So both of these have to be selected by us. Do you agree?
Yes, yes.
But mu I and mu k, I can take mean of all the data points. This is the idea, sort of, I'm trying to say. Do you agree? But
Acha, yes, yes.
because that is a centroid. But my problem here is, even if I know, how will I cluster this? How will I say that I will be able to cluster this? Say I even know the representative elements, something I do know. But clustering here becomes a very, very difficult problem because mu's are also not known, clusters are also not known. So this is a hard problem to solve. Why? Can you tell me how many? So a naive algorithm, what will be the complexity of the algorithm? So what will you try to do in the naive algorithm? Now you will see the feel good factor. You will not know any of these data points, right? You would not know the colors of these data points. You will have to cluster them later on, right?
Yes,
So
yes.
so now what happens is, so you have four clusters. Say you want to say k equal to 4 is known to you. Now you have four boxes or dot 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 k boxes. For each data point, I have k options, right? You're counting first class for each data point. For
Acha.
each,
And for putting a new data point.
correct. For each data point, I have k options. No, data points are given to you. You want to put them in one cluster, right? Say you say name them one cluster C1, C2, CK.
No,
These are
means
the
this is possible if clusters are already formed. Means
clusters are not formed. Think that you will be, these are the sets that you will be making, and then you will decide what are the clusters. They are K sets.
okay, okay.
So for every data point, you will have K options to put them into K clusters. So number of ways you can cluster the data is number of ways.
K to the power n.
Exactly. You can cluster is K to the power n. So out of this K to the power n, one is the best, right? One configuration is best. Do you agree? After you have categorized this, mu1 will be the centroid of C1. Mu2 will be, this is why I did not write the mu's, because they will be derived from the clusters. Okay, did you understand? First, get the clusters and you will get mu k as the centroid of cluster K. Do you agree? Any questions?
No, no. Okay, yes.
So now you will see that you will have many configurations. You will have configurations that you will name this cluster 1, you will name this cluster 2, you will name this cluster 3, and so on. But you will see that these are bad configurations because the means of these clusters will be very far away from one another, right? Only when you get this above configuration will you be able to succeed, right? And that is 1 out of K to the power n. Do you agree?
Yes.
So you see that it is a it's a NP hard problem, right? Or it is intractable problem, intractable. That is, it cannot be solved. Intractable, can't be solved. Solved as n increases. N and k increases. Especially n increases. This exponential time algorithm, we do not want to solve exponential time algorithm. Therefore, the simplest algorithm that we will see, this algorithm that I'm going to tell you now, the k-means algorithm. Day after the 2 classes from now, the last class, 24th session, this is to 22nd, 24th session, we'll be seeing an algorithm called expectation maximization. And we'll see that the k-means is a special case of that. For the time being, let us forget that. But this is just a heads up. That's the best algorithm that I'll be teaching you. And the k-means is just derived from that. So the k-means did not land from the air or something, but this is a very intuitive. K-means itself is very intuitive. So what does k-means do? K-means does a very simple thing. See, since I do not know the data points, right? So I do not know mu k's. So what will I do? See, I have these data points. Let us take 2 clusters for the time being. I take 2 mu1 and mu2 randomly. I select. Okay. So this is called the expectation step. So we'll see why it is called the expectation step next time. But in this expectation step, what I do, can you tell me what do I do? Very simple algorithm. Say I have these 2 mu's. These are my representative elements.
Okay, calculate expectation of the distance from all points to that mu1.
You are this here. There is no expectation. We'll see. Expectation will come in when we are doing GMMs. That is a special. This is a special case of GMM, Gaussian mixture models. So we will see in the expectation step. This expectation turns out to be. This will give you the arg min. Okay, of mu I minus x. Okay, this is the class of x. a cluster of X. Look, okay. What does this mean? It means that assign X to the closest representative element. Okay, do you agree? So for example, this data point will be assigned to this cluster. This will be assigned to this cluster. This will be assigned to this cluster. And similarly, this will be assigned to this cluster. This will be assigned to this cluster. This will be assigned to this cluster. And say this cluster will be assigned to this cluster, right? At this step, this will do for all X. Okay.
But the other one thing, like we don't know the
Yes.
clusters, then how many muis we will
We
set?
don't know the clusters. Very good question. I'll come to it. For the time being, let's say we are selecting that we know the number of clusters. For the time being, let's say that. Okay.
Okay.
Don't be so sad. I am not saying I will not tell. For the time
Nah,
being,
nah,
let
okay,
me.
okay, okay.
Don't be so sad. Okay. This is clear, right? Where you will assign the data points to the closest representative element. Okay.
Yes.
So here I am not saying say k is given. I'm not saying k. So c1 2 dot 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 k. So I'm just writing a generalized form instead of 2. Next step is called the maximization step. Maximization step. And don't think about why are these called these steps. We'll see when we do GMM. But the idea for the timing, even forget about these two names. But it's good to have these two in mind. So that's why I'm naming them. Now reassign in this step, reassign the representative elements. So you see, whatever we were doing in the previous case, we broke it up into two parts, right? Previously, we were putting all the clusters and checking which was giving the minimum distance between the means. But here at every step, reassign the representative element. What will happen is you will take mu I to be the centroid of xi belonging to cluster I, or x belonging to cluster I. What is 1 by number of points in cluster I x belong to Ci, or I can just put the size of this set, right? Is it okay? Do you agree? Say these 4 points, these belong to this cluster, so I will be reassigning this mu to the average of these. Understood? First step, I tell and then you repeat 1, 2 until convergence. That is when no more clusters, when no more data points change. Change from one cluster to another. Or you can stop say after say k n epochs in n steps. This is also a hyperparameter. Is it clear?
The like one thing to clarify, the clusters were
Yes.
not known. We knew only K.
Yes.
The clusters we got by mu i's, those are
Yes.
those are nearest
Very
by
good.
mu i's.
This
And
will give you
now,
wait. So you're saying it's good. These will give me clusters at step I. Step I. Clusters at step I. This step will give me new representation of the clusters. Now tell.
acha, now and here we will again reassign mu I as the centroid of the cluster, which we have collected.
Exactly. Exactly. But this will continue, right? So if you have, say,
But there is a
something
problem
like
that
this,
clusters can overlap.
yes, something you like this, and then you had a point like this and a point like I'm not drawing it very well. Just bear with me. I'm drawing points where it will be easy to categorize. Say you have these data points and these data points. You had one mu I somewhere over here, another mu I somewhere over here, or somewhere over here. So you see, you may see these as the at one step you may see these as your or these as your data points, right? Correct. This may belong to this and the other may be like this. Okay. Agreed. Then when you reassign this cluster heads, what will happen? Your mu has become somewhere over here, but your this point will move somewhere, say over here. And at this step, maybe this is just a cartoon, you will be categorizing this here and you'll be categorizing this over here, whichever you wanted, right? Yes or no? Are you following? So you reassign the mu's and then again calculate the distance. And again reassign the data points and again calculate the. So for every step you reassign the clusters, make the clusters again and again, and you make the means again and again. And it is shown that it will converge. We'll see in expectation maximization why it will converge.
Acha,
Clear?
acha, acha. Okay, yes.
Is this clear? The algorithm is clear, right? So if I give you some data points, what will you do? First step. Step one is
Like you have given the mu i's also. So
select mu i's. Randomly select mu i's in the range of the data. Okay. Then
yes,
what will you do?
for each data point, I will give a mu I to it according to the
Mu
minimum
I, no cluster
distance.
to it. Mu I is the representative point of the cluster.
Acha, acha, cluster to that I,
Yes.
and we will thus get one. Each point belongs to some cluster we have got. Now we take
Yes.
the average to take the centroid of the cluster, and
Yes.
again start labeling according to minimum distance
Until
value.
convergence. So this is very intuitive. So you have an assignment in assignment 4, you will be implementing this, where you will be trying to implement k-means on a handwritten digit data set. And very nicely you will be able to see the clusters being spanned in the data set. So this is the algorithm. So I have written down the algorithm over here. Start with k random vector, the iterate under convergence, each step, assign it, m step, reassign the selector by the average of the points. All these are done. So now,
Dada, like, can
yeah,
you wait for a few seconds? I'm facing a network issue. I'm rejoining.
yeah. So what I'll try to do is session 24. So with the problem with k-means is what I see is the first problem is so we told that it converges. Yeah. So we said that k-mean converges and we'll see it in session 24. and we are trying to see what are the problems with k-means. So there is a problem with k-means you may have noticed for the time being that these are not exactly problems, but these are limitations. You can think about it as problems, but they're generally very subjective. Clustering is very subjective. For example, if I ask you this, what will you say? Will you say that this is a cluster, this is a single cluster, and this is the one cluster? Or say you will say this is one cluster and this is one cluster? There are many options, right? For clustering, you do not know what is the correct option, but we'll try to like categorize somehow. Do you understand? So the idea is k-means does not guarantee unique clustering. It doesn't guarantee unique clustering. Right? Can you see this thing? Is this, can you hear me? Hello?
Yes, yes.
Okay. So k-means does not guarantee unique clustering. Why? Say I will copy this and will show you. I've already got the centroids written there, so you can check that as well. But let me do it once again over here. So you get this data point, right? So in this data set, do you agree? If depending on where you start from, say you may have started from here, here, and here. So in this case, you will get these two as your clusters. Do you agree? On the other hand, you may have started from somewhere here and here. Then you will get these two as your clusters. Do you agree? And it will converge there. It will not change. Do you agree? So, for example, I have written mu1 as 0.0, 0.8. And mu2 as 1, 0.2. So these two can be one configuration, the other configuration. So this configuration will give me which data point? So mu1 0.8. What will you get as the clusters? Can you tell me? In this configuration, if you start from the mu's?
Like 0100 and 1011 as
These two? And you will converge? Yes or
uh-huh.
no?
Yes, yes.
Similarly, if I take mu1 as 0.8, 0 and mu2 as 1, zero point 0.2 or 0.2, 1. Now clearly you will get these two as the clusters. Yes. Because this will be reassigned to 0.5, 0, and this will be reassigned to 1, 0.5. Yes or no?
Yes.
Is it clear that clustering k-means need not guarantee unique clustering?
Like, will the same happen if there are many data points? Because here are very few data points, so
No, many also few. So this is a way to prove. If you have to disprove, if you have to disprove, one counter example is enough,
acha, acha,
right?
yes, yes.
You can take any data point, any number of data points, it will still happen. You can try. So normally what is done? K runs of K means is done. N runs. And you see which is better. Which is better based on the this measure, right? The distance, the total, if we represent this as the loss, right? Once you get the clusters, you can calculate the loss, right? I'm
Yes.
writing down the loss again, C1 CK x mu I square. You can see, you can do n runs and see which is better, and you use that as a, this is the hyperparameter you need to do. Parameter, select the best cluster. So best set of clusters. So, but this is also another, there is another problem with it. You can be stuck in local optima. Right? So this is why you may have to do n runs, that is randomly initialize n times. So normally if there are a lot of data points, I think it's not required if it is in a low dimensional space. Say 2-dimensional space and you have 20,000 data points, then you don't require. But if you have very, very high dimensional space, then definitely you will be requiring. Okay. Randomly initialize n times and then select the best cluster. Now it can be stuck in local optima also. Let us draw this. I have already drawn one example. Very nice example, you can see. And this will also help you understand why you need to do many times. But till today, K-means is such a good algorithm. You just use variants of it. Always remember that, because that's the best you can do. Even if you use neural networks and so on, you will be doing, the idea is based on K-means. So always remember K-means because it has very good mathematical foundations. We'll see in session 24. See this one. When I draw these clusters, do you agree that this would give me the minimum loss will be here, right? This is the centroid of two triangles. Will we have the minimum loss if you are trying to make two clusters?
Yes.
Do you agree? But say by construction, if you by the use of these mu's, say your mu ended up somewhere over here and your red mu ended up somewhere over here. Do you see that it will not change anymore? Say this distance. I'll maybe redraw this in a better way. So this is D1 and this is D2. D1 says less than D2. Okay. So D1 is less than D2. So it has converged, right? Yes or no? Can the means change anymore? Can we reassign any? The means only change when you can reassign. Can you reassign?
Acha, acha, already it has reached the means.
Yes, you can't reassign. Reassign as, say I name this data point 1, P1, P2, P3, P4, P5, P6. If I ask you what is the cluster of P1, you will say Say I name this cluster C1 and this cluster C2. You will say C1. And you will not be able to change it, right? Always it will be the same. Cluster of P2 will be C1, right? C1 to 4 will become C1 and 5 and 6 will be C2. Do you agree? So once the algorithm has converged, it can't reassign data points to new clusters. Data points to new clusters, right? Hence, clearly, it can stop in a local minima. Understood? Any questions?
Like the convergence here means mu I which are obtaining that is equals to the average centroid.
Yes.
Calculated
Yes.
centroid.
So first step, what do you do? Assign the data points, right? Assign data points to a cluster, right?
Yes, yes.
In second step, you set the representative element as the mean of the data points, mean of the points in the cluster, right? Using use it to the cluster whose representative element is closest to the data point, right? Yes or no?
Yes.
So once you have assigned it and you have taken the mean of it, and you see that again, so after 2 you do 1, right? You do keep on doing this. So configuration at, so if I tell you that C1 T plus 1 is equal to C1 T or CIT for all I from 1 to K, what does it mean? So this is the time, T plus 1 iteration, that the configuration
Acha,
has remained.
clusters will not change anymore.
Yes, the clusters have not changed anymore. So the means will also by design remain the same.
Okay.
We have seen, now I'll just put by design 1 by CIT, x belongs to CIT x, which is equal to mu IT. Yes or no? The means will also not change. Once the clusters don't change, means also don't change. It is trivial. You can see that trivially. I just proved it also.
Yes, yes.
So then you will not be able to change it. You will be stuck there, right? Wherever you are there. Wherever you have got that configuration, it will be stuck forever. Agreed? Because none of the steps is changing any configuration in the code, in the state of the algorithm, right? Yeah. So now there is another problem with k-means. The last problem with k-means. This is a problem many papers have tried to address. Another issue is the problem of outliers. So if you have one outlier, your k-means algorithm will suffer very badly. Just see, you have something like this. A few outlier points if I have, say I have to do 2 clustering. I have one outlier like this. Normally, what would a good algorithm try to do? It will just not consider this and cluster these two, and maybe assign this to another cluster just for the sake of it, right?
Yes.
But your means, since are set on using these, what happens is your entire representative element changes. So if your means are somewhere here, you may end up having clusters like these, right?
A big shift in the mean
Yes.
centroid.
Few outliers can totally destroy the clustering. As we can see over here. Although we should have clustered, as we have seen, some points like this, the white one, this should have been the ideal clustering. But K-means would make this as my cluster. Due to one data point. K-means suffering from outliers. So normally you would be using K-means, but you will maybe remove outliers first. See which is out of one standard deviation, 3 standard deviation away from the mean. So there are techniques like remove greater than 3 standard deviation of the data, right? Something like this you can do. We have seen in our statistics class that above 3 standard deviation, 99.9% of the data will not be there, right? Yes or no? So you can be removing those small data points. But so this is one. So for this, people also came up. So now one question you asked, how to select A, right?
Yes.
So this is very simple. You can select K by, say you do not know the application. Say you start from K equal to 2 dot say 50 you want to test and perform the clustering. Again, see the loss, right? Whichever gives you least loss, select that. Okay.
Yes.
So this is like hyperparameter tuning, right? You will be doing in your assignment 3, how to select hyperparameter. You have a cross validation set. On that, you see a metric and decide on a model. That's the idea. This is the hyperparameter. Hyperparameter. What is a hyperparameter? I told you once. Do you remember? What is a parameter? I have also told that also. The first day, first class, I told of machine learning. Parameter is
Parameter means that theta or that input means.
good, very good. Directly trained. Trained or the fee or the weights or the hypothesis, right? This is what your model directly trains, correct? The theta, for example, theta, W, so on, right?
Yes.
Hyperparameter is tuned on a cross-validation set. That is the left out set where you see which has the best accuracy on the cross-validation set. And then you use that model on the test set. You'll see this in assignment 3. I think you have shared the assignment. Please use the recent version, which is uploaded today. It's very nice assignment. You just try to do it. I have given deadline till June 15th. Try to submit all the assignment, please. It will be very good, useful. You will learn the entire fundamentals of all these things. There's coding and theory equal weightage. People had told me, but okay. So now people had also come up with new algorithms to solve this outlier detection problem. It was called K-medoids or K-medoids problem instead of K-means. The algorithm is very simple. I will not even spend like 10 minutes doing it because it's once you have understood K-means, K-medoids is a simple, small, very simple algorithm. Generally, what is is done is, so we know this, right? This is our empirical loss. Do you agree? Instead of the norm, I wrote distance. D is a distance measure. Okay, we are starting with K-medoids algorithm. K-medoids algorithm. We were using mu I over here, right? In K-means. Do you agree?
Yes.
Now I will say that to deal with these outliers, I will select a data point in the training data itself. Data as a representative element. Now you see, once I select a data point in the training data as a representative element, my problem of outlier is solved, right? I will be seeing which data point has the minimum distance from its people who will be belonging to it, right? The
Please repeat.
fundamental idea, I'll just say, instead of mu i's as, or that is the centroids of the centroids, I will use data points or true data points as the representative element. Okay, this is the idea. So now I'll draw this figure and then you'll understand. Same example I'll draw. Okay. Now, say instead of selecting the mean or the centroid of these clusters, let me select one of these data points. So let me select this data point. Let me select this data point as the representative element. If I select the data point, so this is exactly like the naive trust going towards the naive algorithm. Do you agree? If I select one data point, I calculate all its distance from it. I am very unlikely to see effects of outliers because from this will never be used as a representative element, right? Because it's very far away. This sum E will become very large. Yes or no?
Acha, means till now mu I may have been in the data set or not. Now we are taking points from.
Mu I is the mean, right? It will be the average of all the data points.
Acha, it may not be a data point. Yes.
It is not a data point anytime. The probability of it being a data point is 0 because it's an R2 space. It is 1 point. Right.
Yes, yes.
So you see, you were getting these, and then this was the problem. This was your K-means centroid. But now I'm not going to take centroid. I'll be taking representative elements. So if I take this green point, I'll be getting these clusters, whatever I wanted. You see the distance. So I name this cluster, this point O. O to X is the maximum, right? Yes or no? For all X. I have written like that. I have drawn X or the O point, okay? Or very large. The distance is very high, right?
Yes.
Outlier O say all data points have very, very high distance. So I will never be selecting that as my cluster representation, right? Because the distance I have to minimize. I have to minimize this. Right? Okay. So this is very high and you will not select it. So you will be ending up selecting points that are in the clusters, the representative elements. So outliers will be handled. So we'll let us take an example of how to do this and then you'll understand the algorithm. So how do you do this? So how do you select? So what till now, what did we understand? So we will be selecting, say, K. If there are K clusters, how many representative elements will we select?
K.
K. So now let us take, so select. I have written the algorithm over here, but I will not go through the algorithm first. It will be like, you'll think that I'm just reading if I do that. But I'll not do that. I'll do this example and then you will understand how to do this because this is more of a, it's not more mathematical. It is K-medoids is very, very design oriented algorithm. It's not, there's nothing mathematics over here. It's just like trying heuristics. So select K representative elements. And then we'll start. And the central idea is distance from the representative element, say OI, has to be calculated. Okay. So generally in K-medoids, what is used? Distance x comma OY the Manhattan distance is used. Okay. Or the L1 norm, right? This is the L1 norm, right? Yes or no? L1 norm we defined as the coordinate to the pth norm is to the power p whole to the power 1 by p. Yes or no?
Yes.
If you are asking me what I am writing, x1, x2 dot 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 x xd are the features, right? You're following this, right?
Yes.
Okay. So p equal to 1 is called the Manhattan distance, and then it is used for, this is used because p equal to 1 is known empirically to work better with outliers. This is why kp equal to 1 is used. Everything is empirical about this algorithm, most of it. So let us see. So now what is the algorithm? You start with two representative element and then calculate the distance of the entire loss that you have. Okay, so let us do it. So I have given you this thing. Calculate the loss if you take the representative elements as O1 and O2 as 0, 0 and 0, 1. Okay, these are the two randomly data points I selected. Okay. So now distance from 0, 0, O1, distance from 0, 0, 1, 1. Yes or no? These are the two data points I have. Two representative elements.
Yes.
Now what data points do I have? I have 0, 0 as one data point, 0, 1 as one data point. Help me fill this 0.1, 0 as one data point.
0.5, 0.5 and 0.75, 0.7.
Yes. So these are my data points I want to cluster. So now you tell me what is the distance? This is 0, right? This is 1.
Yes. 1.
I will write 1 for you so that you will not say that I am not following. Just subtract the coordinates and add them. Add the absolute values. Okay. Clear? I don't need to do for the others.
No, okay.
So then tell me what is this? This is also 1. And the last one is 1.5.
1.5.
Similarly, tell me the distance from O2.
1.
This is 1,
0.
0,
1.
1 or
Hey, 2,
2,
2, 2, 2. Yes, 2.
2,
0.5,
1.
1.
Hmm.
And this is 0.75, 0.25. That means 1.
1. This is 1. This is 2. This is 1. 0.75 minus 0 plus 0.25. That is also 1. Okay. Now I get. Now my clusters I will know, right? Clusters are cluster of a data point X is what? Argmin of I. Yes or no? The minimum, whichever is the minimum distance, you will assign it to that cluster. Yes. Okay. So to O1, which data points belong? Cluster 1, cluster 2. Cluster 1, 0, 0 belongs. Then 1,
1,
0 belongs.
0.
So this is equal. We can select this also. These three belong, right? Okay.
Yes.
So the total so belongs is 0, 0, 1, 0 and 0.5, 0.5. These are so to cluster. I'll just draw it over here in some time, but just bear with me. In cluster 2, 0, 1 and 0.75, 0.75, right? 5 data points are there. Correct. So now after step 1, I know this is my clustering. 0, 0, 1, 0. This is there. Right? So this is what I have. So which data points are together to be clustered? 0, 0, 1, 0, and these three, right? Okay.
Yes.
Based on these representative elements and then based on this representative elements. Now, what is done? You do this randomly n times, keep on doing it. But this is where the algorithm is a bad algorithm in terms of time complexity. You will select one of these. So previously, which were your representative elements? This was your representative element, and this was your representative element, right? Okay. So remember what is the entire loss of this E of this configuration? This is 2, right? And this is 1. Do you agree?
Yes.
So E total is equal to 3. Do you agree? This is nothing but the sum over I equal to 1 to k, x belonging to cluster I, d of x, comma oi. Clear? This is my E total. Right? This I just
Yes.
added the distances. Good. So now in this algorithm, what is done is, so first I have calculated the distance. I have done this. Calculate. So you next steps to step 1. This is step 1. Step 2, select one representative element. Very bad algorithm, but it still works. Swap with any other representative element. Why I'm saying bad, I'll come to it in a moment. If k becomes large, again it becomes you will have to do exponential time calculation, because it is exactly the naive algorithm that we are trying to do. But it's just like selecting randomly on expectation, you will get something. So that's the idea. Okay, swap with any other representative, any other non-representative element. Okay, so now say in my question, I'm telling your new data point, say, is this. So I give you this as my new cluster, which I have not yet drawn yet. So yeah, so this 0.5 comma 0.5, I'm making my new cluster. Okay, this is representative element. I'm keeping this the same and changing one of these representative element. Okay, clear?
Dada, like I was facing a network issue. Can you say how you change the representative
Randomly,
point?
randomly.
Acha, okay. Okay then.
But you can also do it for all, checking for all, and it will just take exponential time, right? So if you check it for all, it will take k times. And then again, you will be doing it for k and then keep on doing it. So k square, and then it will go on. It's just the way you implement it. But the idea is randomly select one of these. You can also make it ordered in an order way. But let us see, if we select the new data point is O tilde. So a data point till distance to O tilde. What is the distance? O tilde is 0.5 comma 0.5. So this is, I will let me draw this in a new. Yeah, tell me. So first point is 1, right?
1. Next one is also 1.
Wait 1 minute, I'll just write it nicely. D dot 0.5 0.5 O tilde. Okay, this is 1. This is also 1. This is also 1. Right?
Next one is 0 of
Last one.
0.5.
So now in step 2, you see only what happens. So you can say I select this, I keep, since both are 1, this as a data point and my this as one cluster, right? So now you tell me, once I change this, my O2 still remains the same because I made it my like that, O2 tilde, but my loss changes, right? Right? Can you see? What does this loss, entire loss become? 1.5, right? Or what? I made some mistake.
Loss increases.
I see it increases over here. Yeah. No. 0.75 0 comma 1, right? Okay. True, but I can't do anything. I just, this is what I thought it will decrease by the geometry. Let me just check once again. I think I'm making, 0.75, 0.75. I had calculated to be much higher. I don't know why. Let me just. Two. I think I have written something wrong. Wait. I was right. I'm right only. It will not increase. I mean, I can see from the geometry it should not increase. Why should it increase? I've Yes, it will not increase, no? Ray, you're not telling me. Wait. I didn't reassign the data points correctly, right? After you change this, right? I have not, I have taken 1 instead of 0.5. Just see this. When I reassign, what will be my cluster 1 after reassignment? Tell me. After I reassign, do you agree this will also shift to this cluster? Yes or no? This is 1, it became 0. 0.5 distance to 0.5 to 0.5 is 0, right? Hello, am I audible? Hello?
Yes, Dada.
No, I'm just asking, can you hear, did you understand? Like once I reassign this 0 I didn't see. This is 0, right? This 1 is no longer the closest data point.
Acha, acha, yes.
So 0, 1, 0.5, 0.5 and 0.75, 0.75, right? And C1 will be 0, 0 and 1, 0. Yes or no?
Yes.
So let me write the step 1s in green. After step 1, only this and this will remain.
Yes.
So what is the loss of the first cluster? It will become 1. E1 is equal to 1 and E2 is equal to 1.5, right?
Yes.
So I'll add these two, I'll get E total as 2.5. So now after a reassignment, what do you tell your code? You tell your code, see if E1, E total minus E total tilde, or rather you can write, see the change or the delta ET is less than 0, right? Here it is minus 0.5, right? Then keep the change. Else don't change. Did you understand? Is it clear?
Yes.
So if you see the loss decreasing, if loss decreases, keep the change and iterate until fixed number of epochs, fixed number of steps, fixed steps, or convergence. When you see it is not changing. So find the error in O2. It's a better choice, right? Our loss decrease, so it's a better choice. Let us draw the clusters nicely. 0, 0, 1, 0, 0, 1, 0.5, half, half, 0.75. That's what I was thinking. Why, according to geometry, this should be better, right? So now what are the clusters that I have? I have 0, 0, 1, 0 as one cluster, right?
Yes.
And the other cluster as this. And we'll see that this is the minimum that you can have. You can check. This is the minimum loss you can have. So the algorithm, if you formulate it, can be written as, so if you see the algorithm, repeat, assign all the rest of the data points to the nearest cluster. So we have arbitrarily select. The first step is arbitrarily select k objects in the data set, have representative elements, assign all the rest of the data points to the nearest element, select a non-representative element O randomly, compute the cost of swapping that we see. Yeah, can you hear me? Compute the cost of swapping from swapping O with OJ, whatever you are trying to swap. If less than 0, then swap O with OJ, right? OJ is the new representative element. Okay, is it clear? Is the algorithm clear?
Yes.
So, but what is the problem? The drawback is slow, because this is more like the trivial algorithm. So there are variants of this algorithm where you can select two clusters or similar to that. For two clusters, it will work, but for others, it will not be used. So with that, we have seen the two classical algorithms, K-means and K-medoids. Now we'll be seeing the next half an hour a branch of clustering, which is more like everyday life, called the hierarchical clustering. So look at this figure over here. So I am trying to cluster the food on the basis of taste of this food or the cuisine. So you see, clustering does not always mean that you will cluster into data points, right? Does clustering always mean that you will have to cluster data points like this? It doesn't mean that. There can be clusters within a cluster, right? For example, I'll give you, this is a very nice example that I made. Think about cuisines. And if I had given you, say, Indian subcontinent. This is cuisine. I had given you Indian subcontinent, Africa, Europe, America. Okay. If I gave you clusters like this, do you agree that's let us say for the timing, these are the type of food that we have, right? These are the set of food similarity between food items, food taste, some spices used or the ingredients used. Okay.
Yes.
But see, but Indian subcontinent will have clusters in itself, right? For example, your Pakistan food will be very similar to food in Punjab, but it will be very different from food in Bangladesh. right? For example, even in South, you will see different food in the South. Again, you will be seeing similarity maybe between Sri Lanka and South Indian food. You will see little similarity between East Indian food and South Indian food. But when you compare their similarity across food across the Americas, you'll see that they are similar, right? Is the intuition clear? So you make clusters within cluster. Are you following? So once you
Yes,
follow this
yes.
idea, it's like very simple algorithm. So the idea is make a tree structure. And once you're able to make a tree structure like this, say you have all food divided into Indian subcontinent, Europe, America, then you divide the Indian subcontinent food into India, Bangladesh, Pakistan, divide India into different regions, north, south, east, west, divide Bangladesh into east, west, Pakistan similarly, and then again go to Europe, divide British food is very different from Italian food and so on, right? That's
Yes,
the
yes,
idea.
yes.
You keep on categorizing them, but you cluster them at a higher level. So it's like a so if you told me if I tell you to cluster between continents, you will give me this level of clustering. This clustering is giving you a this is called a dendrogram. This can be used to cluster at any level. You see, you can cluster here. At this level, if you cluster, you will see all the data points somehow. You will see generally three clusters. Similarly, you can also cluster in a sub-level. Then you will be seeing clusters in the leaf nodes, right? And so on. So this you will make a tree-like structure, which will give you first cluster, and then from clusters you will make further clusters. Is it okay? The recursive dendrogram clear to you? The idea clear to you? But how will I make? I'll be showing it now. So therefore,
Yes.
we can, but you can, as soon as you see this, you can understand, right? So I can either divide this food first into these, or I can start off with these food and then make bigger clusters. That's the idea. So the idea is I can make leaf nodes, connect them to make bigger nodes. This is called a bottom-up approach. Bottom-up, where clusters are agglomerated or merged. This is called agglomerative clustering. Agglomerative or top or bottom up clustering, where you go upwards, right? You start from individual food. Say you start from rice, dal, and so on, pulses. And then you try to cluster rice, dal together, and then the fish together, and then you cluster, make a East Indian food. Then you cluster other things together, and then you make it grow upwards. Indian food you cluster together and then put go upwards, right? And then you get all food at the end. Is it clear? Is the overall this is the overall idea or the overarching idea. Once this is clear, this should be a cakewalk. Is this clear? So you take smaller elements and you try to club them. Similarly, you can do divisive clustering or divisive clustering, where you start from everything and then you divide. Right? So on. This is called the top-down clustering. Okay. Any questions? I'll wait for a moment before I begin into how do you do agglomerative clustering and divisive clustering. I hope this is clear. Okay, so let us start with agglomerative clustering. So in agglomerative clustering, again, I have taken an example over here to show you what is the agglomerative clustering, and we'll be trying to understand via the example itself. It will be very simple for you to understand. The idea algorithm I'll be telling in a very simple way, and then I'll show you how complicated is each of these steps. See, calculate pairwise distance between clusters. So you will be tell me, Dada, how to calculate pairwise distance between clusters? They're sets. I'll say wait for the time being. Will be say you know how to calculate it. Then merge clusters with a minimum distance. Is the idea clear? So I'll write this very nicely. At every step, look at this very nice algorithm. Calculate DC, DCJ, CI, CJ are the ith and jth cluster. Then merge CI, CJ such that you will merge them such that it is the argmin okay, whichever minimizes the distance. Some books write it similarity also. Similarity between CJ, CI and CJ will be the inverse of distance or the negative of distance or so on. Less distance means larger similarity. So you can write argmax of the similarity. Clear? Is the overall idea clear?
Yes.
So you see you have few clusters over here, C1, C2, C3, 1, 2, 3. You see the distance between these two clusters. You see this is lesser than the other two. So you merge 1, 2, 3. Let me write C distance 1, 2, distance 1, 3, distance 2, 3. Say I say distance 1, 3 is minimum. So I will merge 1 and 3 to make a bigger cluster. C13, and then I will merge C13 with C2 because that's the remaining. And this is repeated until node is reached. Until the root is reached, right? Clear? But what is stopping us from doing the algorithm? Can you tell me? What is stopping us from carrying out this algorithm?
We
Two
don't know
things.
how to do D.
D, we do not know one thing. Another thing is starting criteria, we do not know. So first step is in the beginning, what do? Select each element as a cluster. Right? This is your base case. Right? Then you can do it, right? Once you start from individual element, then you can keep on clustering upwards. But then how do you do this? Is the question that I have to ask you. You do not know what is D. Very good. For knowing D, there are a few ways to know D. There are two ways. Like say for the timing, let us say there are two ways. What are the two ways? I can define D as, say I have two clusters. One data point here, one data point over here. C1, C2. I can define C1, C2 as the argmin of the distance between Okay. Let me write Ci and Cj for better clarity. What am I doing? Whatever I drew here, I'm trying to show that. So you have data points like this. But this is the minimum distance, yes or no? Okay.
Yes.
This is the minimum distance between these two clusters, right? Like between points between these two clusters. Do you agree? So this
Yes.
is the, so I should not write argmin. You should have told me. It should be minimum, right? The value that minimizes the distance. This is called a single linkage distance. Why is it called a single linkage? Can you tell me? Because it takes into consideration only one link, right? Other, even if some clusters have very far away data points, something like this, it will not even think about them, right? Compared to, say, these two, you have clusters. I don't know why is it not coming on the screen. This is called a, oh no, this is not even, I've drawn another, yeah. You see, therefore, whenever you're linking new clusters now, only one of these data points is enough to link them. Therefore, it is called a single linkage. So you don't need far away data points to be linked in any way. So you will say that why should I consider this? This will give me bad clusters. So I say, okay, you can do another way of clustering. You can consider the, what can you do? You can be a bit conservative and consider the distance between two clusters as the maximum distance. Right? That is also a valid distance. This is saying how maximum far separated, how far maximum, how far the clusters are separated at max, right? It is trying to see how far is the cluster separated at maximum. So this is sort of giving you circular clusters. So you can see, I'll show you a picture in Duda Heart. Here it is. This is the book I was telling you about, one of the books. So you see single linkage. What is happening? It's making what type of clusters? It's just linking closest data points, right? Can you hear me?
Yes.
You can tell me what are you not following? But here you see you have nice, beautiful circular spherical clusters because you consider the farthest distance from one another. You are taking the farthest distance to make. So wherever the distance was the farthest, you merged them. And this is shown at some k, some level. You could, at the end of the day, everything is merged in cluster hierarchical clustering. But it is shown at 4 level where you have 4 clusters, right?
Yes.
But that is clear to you, right? That when you have small things, what happens is, see what will happen. I'll give you a nice example. This will maybe give you a better intuition. You have data points like these. Say you have one cluster like this, right? This will give you a very nice intuition. What will single linkage do? Can you tell me? What would you have done? If you would have asked me, I would have linked these two together and the other as the other, right? Right?
Yes.
I would have felt like that. Many people would not agree with me because clustering is not a unique solution. Everything is right because this was minimum, but this is complete linkage. You're taking the maximum distance. But if you use a single linkage, what would have happened? Should I use the green for the complete linkage? And for the single linkage, you see they're almost close to one another, right? But the closest points between these smaller clusters are at very far distance.
Yes.
So in single linkage, you will be forming this big cluster. Always this happens. You will be making this tailed effect. This is called a tail effect. You make a long series of links. Therefore, it's called a single link. But others, but on a complete link, what is happening? You're understanding. Now there's big one cluster here, one cluster here. You see the farthest distance, so they are more compact to one another. It farthest actually constrains both of them to be close to one another. I'm not saying one is better than the other because complete linkage has a disadvantages. Like few outliers can create a problem, right? If you have a very far, so you have two clusters. If say you have one cluster over here and one data point very far away, I would have tried to link these compared to this, which is I would not have wanted to link, but this far one data point that is over here is going to create this ruckus, right? Do you agree? Both has its
Can you
advantage.
explain this example once more?
I'm saying that say you have one, just if all the clusters are here and you have one outlier, right? I'm not drawing, so this is,
Yes.
so I have this cluster, this two clusters. I would normally have made these a big cluster, but you have one outlier somehow linking them. So then what will happen is in complete linkage, I would only be able to do this. This would happen in complete linkage. Linkage is sensitive to outliers. Okay. It's sensitive to outliers. Therefore, if you remove the outliers, it will work well because you are forcing. Are you getting the intuition that you are forcing? You saw this from this example and also this uh, concrete example where you are trying to force the endpoints of two clusters. You're making them very close to one another by construction, right?
Yes.
But in single linkage, what is happening? You can be as far as you can, but the one class data point in each clusters must be close. Like just like I drew over here, right? Are you following? So both have its
Yes.
advantages and disadvantages. You can use single linkage or complex or the complete linkage, but generally in practice you use an average linkage. You take the average distance between the two data points. That's the most sane way of doing the thing. It's the between path, right?
Can you
So
once repeat what was the need for complete linkage?
you see now this diagram I drew over here. Again, I'm drawing single linkage. If I had, what would have happened? I have this cluster over here, this cluster over here, right? Use this will one. Which do you think should be the clusters? I think these two. I like these two as better the clusters. Matlab next step of clustering.
Yes.
Okay.
Okay, here single linkage will create a problem. Acha.
Yes, because single linkage is like linked at only one data point. So you may have very far away clusters, but they can be just linked at one point compared to very closely related cluster, but still they will not merge, right?
Yes.
Here also, I'll just maybe contrive this a bit more. Yes, this. So again, you will see that these two will get clustered. Very bad. This is the bad thing. On the other hand, complete linkage is the outlier problem. On the on in practical purposes, what do? You take the average of all the distances. That's the idea. Now if you have understood this, let's do it for a complete linkage. Let's solve this. Your homework will be try to do this with homework. Try single linkage for this example. I'll do complete linkage, the more complicated one. Let us do it. And I told you to use L2 distance to compute it. Once you're free, please look at the assignment also. It will give you a lot of confidence once you solve it. And anyways, you're going to get certificates from Jadavpur once you complete the course. Last time also people have got, you can ask the previous course. But for that, you need 70% marks. Just to tell you. People who have attended will get 10 marks because my mark out of 110, 10 marks would be grace for, not grace, would be on attendance bonus. Let people know. Okay. So this is the thing that I have. I need to calculate the distances. So I'll start off with, let me just do this. First slide the data points. How many data points do I have? 0, 0, 1, 0, 0, 2, 1, 3, 3, 2, 3, 1. Okay. So I have 1, 2, 3, 4, 5, 6. 6. Okay, good. 0, 0, 1, 0, 0, 2, 1, 3, 3, 2, and 3, 1. Can you tell me what type of a matrix will this be? Distance matrix be?
Symmetric.
Will use, yes, L2 distance. So we can only calculate the upper triangle. And I don't even need to calculate these distances, right?
Ha, 0.
Why is it? Have I missed some data point?
You have drawn 7 cross 6.
I see. Ah. Re, 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 re. This is okay. Okay, now let us write the distances. So what is the distance between? So I'll be using d square as x2 minus x1 squared plus y2 minus y1 squared. Right? This is going to be my metric, L2 metric, a square of the L2 metric, because it's a square is a monotonically increasing function. I can use square, it doesn't matter. So what is the distance between this? This is 1.
1.
Between 0,
4.
4. 10. 13. 10.
Yes.
Tell me the second line. I'll just write
It's
1 for the
5.
complexity. 1 minus 0 square plus 0 minus 2 square is equal to 5. 5. This is
9.
9. This is 8, right?
Yes.
This
5.
is
5.
5. Next is 0, to say this one this is 10 or 2. 2, right? Yes. 0, comma 2, say 1,
9.
comma 3. This is, yes, this is 1 square plus 1 square, 2. Then we have 9, right?
Yes, 9.
Then 10.
Yes.
Then we have 1, 2, 2, 1, 5. 5, 5,
8.
right?
Yes, 5,
5.
8.
2, 2, 8, correct. And this is 1, right? So I will select the minimum distance. This is starting is very simple, right? I can select the minimum distance here. Only one data point is there. Single linkage, complete linkage, average linkage, everything is same, right?
Yes.
So I will select. I have 2 minimums over here, and this will give me clusters already, and 3 actually. See, 2 also is there. I will not get any minimums. So I'll get 3 clusters. I have done it deliberately for that. So these 3 I will select, and I'll make 3 clusters. What are the 3 clusters I'll make? C1. C1 will be, let me write it down. Say C1 is 0, 0 and 1, 0. Okay. C2 is 0, 2 and 0, 2 and 1, 3. And C3 is 3, 2, 3, 1. Yes or no?
Yes, yes. Okay, yes.
So I am making, so based on this minimum points, I am making 3 clusters. 1, 2, and 3. Okay. So now I will be writing, instead of data points, I will be making a new matrix, right? New matrix will be on what would be the shape of the new matrix? Step 1, step 2.
You are using single linkage here.
Complete linkage. I will not make the, you can make also, you can help me, but I'll try to do it one full and then you can fill up the table. We need to fill only 3 elements right now.
Acha, yes.
C1, C1 is 0, 0, 1, 0, 0, 0. Let me just write C1, C2, C3. It will be easy for me. I don't want to write so many times. So I might have my C1, C2, C3 written over here. Okay.
Yes.
So now you tell me what is the distance between C1 and C2. This is complete linkage. Complete linkage will tell me this is distance. This is the
K9.
maximum. Yes, maximum between. Let me just write it down. Maximum between D0, 0, 1. I will write 0, 2, comma, distance between 0, 0, 1, 3, right? Yes or no?
Yes.
1, 0, 0, 2 and 1, 0, 1, 3. So we are trying to see all the pairwise distances. How many pairwise distances will we have? Ci into Cj, right?
Yes.
Okay, so 4 pairwise distances. Let us write max of 4, right? 4, 10, 5, and 9. You said 10, right?
Yes.
Good. Good boy. Next, C2, C3. C2, C3 will be, let me write it down. DC2, C3 is the max of, let us do 3 square plus 2 for 3 square 9. Then t square 10, 2 square plus 5, right? These two data points, 1, 4 square plus 5,
8.
5 and 8. So this is also 10. And DC1, C3 is max of 0, 0 is 0, 0, 0, 2 is 4, 10, 5. Correct?
4, where did you get?
I don't know. C1, C2 is 0, 0, 0, 2, right? 4,
30.
13 where? I'm not calculating correctly.
Yes.
Oh, 1, 3, 1,
C1.
3. I am doing 1, 2 again. Sorry, sorry, sorry. Good, good. You're following. I did 1 and 2 again. 13, 10. Then we have 2, 2, 4, 8 and 5, right?
Yes.
This is 13. So now we clearly see we can either cluster C1 and C2 or C2 and C3. Correct?
Okay, yes.
So I just say I cluster C1 and C2 and C3 and I will be done. So now my entire dendrogram, if I tell you to plot, let me do it at the end. I'll just put these this together. Okay, let me draw it here only. What can I do? So you have 0, 0, 1, 0. Then you have 0, 2, 1, 3, 3, 2, 3, 1. We clustered these two, got C3, right? We clustered these two, we got C3. We got C2. We got C1, correct?
Yes.
And then we clustered 1 and 3. Hey, it will not look good. I will not cluster 1 and 3 because it will not look good in the dendrogram. 1 and 2 I will cluster.
It was 2 or 3 or maybe 1 or
2 and 3. Then it is okay. 2 and 3 I can cluster. And at the end, only 1 is left, so I will just merge them. Okay? Understood? You can do the single
Yes.
linkage now.
Yes.
Please try it and share it on the group if you want, of course. 1302 at these two. So what did I do? I clustered these two first. These two, this was the step 1 of clustering. And in the step 2 of clustering, what did I do? 0, 2, 0, 2, 1, 3. I clustered these two, right? And step 3, I clustered everything. Right?
Yes.
Step 1. So with that, we have almost ended. In last 3 minutes, I'll be showing you what is meant by divisive clustering, and that will end our clustering algorithms. And next day we'll do dimensionality reduction. That is much more interesting and mathematical. So in divisive clustering is what will happen? Can you tell me? So agglomerative clustering had some foundational theory to it. In divisive clustering, what will happen? So we'll start from all the nodes, right? And we'll try to break them up. Okay. Is the idea clear? So you start from all the nodes and try to break it into, and you stop at the end. You have to put a stopping criteria. And this is where it gets very tricky. You have to select stopping criteria. So people generally use agglomerative clustering. They don't use divisive clustering. Okay. But this is also a good algorithm. You can use k-means in it in some way. Let's see. And you can use any clustering. So the idea is start with the entire data set, divide the nodes into k child nodes using some flat clustering method. Flat clustering means that groups into different clusters like k-means. Then you repeat for every node these steps. So let us see one example. Is this algorithm clear? Like it should be instantly clear. So you have, say, one cluster like this. I'll draw this, it will become very clear. Right? You can see this cluster. So I divide this into two clusters.
Okay.
And how will I divide it? That you will tell me. How will I divide it? You know already one algorithm to divide it.
Acha, we like K means one.
Good. Good.
But what about if we divide the whole into means many clusters
You
at
can
the
do that.
first
That is
node?
also, you can do that. K is a choice. You can do 2, 3, 4, whatever is suiting you well. You can do that. Depending on the, again, a hyperparameter to tune based on your application. You have to see what is the distance, what is the clustering you're going to get. There are many, you'll get clustering at one level, right? You'll get those. So at one level, you say you are interested in this level, what are the clusters, right? And then see the distance at that level, correct? You will have to
Clusters.
stop at one level. For example, you can stop, make these two as my clusters, right? At any, this is the help of a dendrogram. At any particular point in time, I can divide my data set into n number of clusters. Right, layer 1, I would divide this. Layer 2, I'll get 3 clusters and so on. Understood? Depending
Yes.
on the, so the, and then you see which has the minimum distance. So now let us see for this example. So we will start off with, I am selecting k equal to 2 for just demonstration purposes. You can select anything you want. So that makes it tricky compared to agglomerative clustering. Agglomerative clustering, you do not require all these heuristics where you need a single linkage, multi-linkage heuristic, but you do not require this heuristic where you have to select how many clusters you're breaking, what is the stopping criteria, right? Okay. So now I divide into two k's, k equal to 2. Say I had a mean over here, a mean over here. So tell me which two, what do you want me to cluster? Say,
Like 0, 0, 1, 0 and 0, 2.
yes, I can, these two will become cluster, one cluster by its definition, and these will become one cluster. Okay. So I will
Yes.
be getting 0, 2, 0, 0, 0, 1. And this is again k-means. So you can have multiple, depending on the runs, you can have multiple k clusters, right? at every step. It doesn't depend on, it is not going to be unique.
Yes.
So you have to again run this multiple times. Again, I select, say, these two I cluster. So I'll get 3, 2, 3, 1, and 1, 3. Then finally cluster these two, 3, 2, 3, 1. This you divide, say you get one cluster point over here, you cluster these two, 0, 0, 1, 0, 0, 0. I'll square the leaf nodes. At every step, do k-means, k equal to 2 recursively. Okay. So with that, we can, if you do not have any questions, we can stop. The next day, we'll see dimensionality reduction technique. These were all the unsupervised learning algorithms that we had. Dimensionality reduction can be both unsupervised as well as supervised. We'll see both of them. One would be PCA, which is unsupervised, which will be used extensive in your life. Whatever you do, PCA has to be used. And the second one algorithm would be LDA, which is linear discriminant analysis, which is also like a classifier, but also a interesting dimensionality reduction algorithm. We'll do next time. But today, do you have any? And with that, we'll end all the GATE syllabus. And in the last class, we'll get a bonus session and we'll do expectation maximization just to put you in the bridge of the next level of learning. Okay. Any questions regarding supervised, unsupervised learning? Any clustering algorithm you have doubt in? Okay, if no more questions, I'll stop recording. Okay, anything you want to